where we had left off at the end of Monday's lecture was we had figured out that we could represent time domain sinusoidal voltages. So let's say that V of t is a voltage that can be characterized by Vm cosine omega t plus some phase angle theta v. I of t equal to some current Im cosine omega t theta I. These relationships are how we describe sinusoidal signals in the time domain. Okay. I had shown you that this sinusoidal voltage was the real part of the following complex voltage, Vm e to the j omega t plus theta v, and our sinusoidal current I of t could in turn be expressed as the real part of this complex number, Im e to the j omega t plus theta I. And I'm going to call these complex number representations the mixed domain. One thing that I want to be very, very clear about here is that our time domain representation and our mixed domain representation include the exact same information, right? Because we're characterizing our sinusoidal signals and our exponential complex signals by their magnitude, their frequency, and their phase angle. And those three pieces of information are common to the time domain representation and the mixed domain representation. Okay. So what I'm going to introduce today is a frequency domain representation of these signals. Okay. And I may also refer to this as the phasor domain. I'm going to use these two terms interchangeably, frequency domain and phasor domain, okay? So before I give you your equations here, I want to talk about what a phasor is, all right? So a phasor is simply a shorthand notation that electrical engineers have created in order to represent these time domain and in turn mixed domain signals, okay? They are complex numbers expressed in polar form, meaning that they have a magnitude and they have a phase angle. They do not, however, have a frequency associated with them, okay? Now, the reason why we can get away with effectively throwing away the frequency portion of our time domain and mixed domain representation of these signals is because it's common to all signals. So going back to our topic of forced response, if we have an excitation function that is oscillating at a particular angular frequency or a particular linear frequency, the response, meaning the voltage and current across any component, will all oscillate at that exact same frequency. So we suppress that frequency term by literally just throwing it away because it's redundant information. Since it's common to everything, it doesn't actually add any value to our analysis for the most part. All right, so our frequency domain representation of a voltage is going to be V with a bar over it, which represents a voltage that is a complex number. And the only two pieces of information that this phasor representation will have is a magnitude and a phase angle. Similarly, we can represent phasor currents by their magnitudes and phasors. Okay. So I am of the opinion that this is a fairly straightforward process, but just in case somebody is not quite catching what I'm throwing, we're going to do a couple of quick examples here to illustrate some points, okay? So let's say that we have a signal VA of t is equal to 8 cosine 11t plus 10 degrees. The phasor representation of this voltage, VA, with a bar over it, would simply be 8 angle 10 degrees volts. We keep the magnitude, we keep the phase angle, we throw everything else away. All right. Now, let's complicate things ever so slightly. Let's say that we have VB is equal to 11 sine 2 pi t plus 30 degrees. Our phasor or frequency domain representations are always based off of cosine functions because they represent the real part of that complex or mixed domain representation. So in order to convert this signal to a phasor properly, we would first have to convert this into a cosine function in the time domain in order to do this, okay? What would VB of t be expressed as a cosine function? Subtract 90 degrees from the phase angle. So that would be 11 cosine 2 pi t minus 60 degrees. And therefore, our phasor voltage VB would simply be 11 angle negative 60 degrees. Lastly, and this isn't something that we'd actually see very often, but you do have homework problems on it, so I just want to talk to you about how to do this quickly and efficiently. Let's say that we have VC of t is equal to 6 cosine 3 square root of 2t minus 15 degrees minus 4 sine 3 square root of 2t plus 75 degrees volts. So we have a combination of sinusoids, okay? Now, since these sinusoids are oscillating at the same frequency, we could apply several of those trig identities that I talked about in Monday's lecture and combine these into a single sinusoidal function and then move that sinusoid into the frequency domain. That is absolutely one way to do it. It is the worst possible way to do it, okay? Instead, we're going to make sure each part of this is a cosine function. Convert the cosine parts into the frequency domain and then do the math or the combination in the frequency domain, and we'll get the exact same result as if we had done it the long way using all that terrifying trig, okay? So the 6 cosine 3 square root of 2t minus 15 degrees part gets to stay the same because it's already expressed as a cosine function. And as Mr. Stubblefield mentioned a moment ago, all we have to do to convert a sine function into a cosine function is to subtract 90 degrees from its phase angle. So that would be minus 4 cosine 3 square root of t minus 15 degrees. Well, crap. I shot myself in the foot here because I wound up having the same phase angle for both things, so we don't actually have to do any complex math for this part. So I'm going to fix this. I'm going to call this 76 degrees. My apologies for not thinking ahead quite far enough there. So now that they have different phase angles, we can't simply do a direct combination. So I could say now that VC is going to look like 6 angle negative 15 minus 4 angle negative 14. And we can put this in our calculator and express it as a single phasor. And to me, that looks like 2.002 with an angle of negative 16.998 degrees volts. I somehow accidentally made my screen smaller. So make it back to bigger. There we go. Sorry about that. All right. So converting from the time domain into the frequency domain is fairly straightforward. Converting from the frequency domain into the time domain is very straightforward as well. The only thing that we have to be careful about is that we need to know what omega is in order to do it. Okay. So what I mean by that is, let's say that we have this phasor voltage Vx, and it is 10 angle 5 degrees volts. This is representative of 10 cosine 2t plus 5 degrees. It could also be representative of 10 cosine 8 pi t plus 5 degrees. It could be representative of 10 cosine 130 t plus 5 degrees, etc. All of those 3 different time domain signals are represented by the exact same phasor because we throw the frequency term away. So we don't take into account omega. So converting from the frequency domain into the time domain requires us to know what omega is, because that piece of information is not in any way, shape, or form included inside of the phasor. Okay. All right. So what I would like to do now is to develop phasor relationships for circuit elements. All right, so let's start with the case of a resistor. So we have some resistor R over which a voltage V of t appears and a current I of t flows. If V of t is a sinusoidal signal, Vm cosine omega t plus theta v, we know that this is the real part of Vm e to the j omega t plus theta v. And finally, we also know that we could represent this as a phasor voltage V, Vm angle theta v. And our current I of t is going to have the exact same relationships. I m angle theta I. Okay, we've done our bookkeeping here. I just want to make you aware of effectively what we're going to be doing here. All right, so my question to you guys is, in developing these phasor relationships, what is the current voltage relationship for a resistor? R is equal to V over I, or V is equal to I times R, Ohm's law, right? So we know that V of t should be equal to R times I of t. So what I'm going to do here is I'm going to substitute in my mixed domain relationship. Okay? So that means that we can say Vm e to the j omega t plus theta v is equal to R times Im e to the j omega t plus theta I. Simply directly substituting in our mixed domain relationships here. What I'm going to do now is I'm going to split my exponential functions up. So e to the j omega t plus theta v could be expressed as e to the j omega t multiplied by e to the j theta v, right? So if I wrote this as Vm e to the j omega t e to the j theta v, I could make the right-hand side look like R times Im e to the j omega t times e to the j theta I. And we can see very clearly that the frequency term shows up on both sides of the equal sign, and so they can effectively be suppressed or canceled out. Leaving us with Vm e to the j theta v is equal to R times Im e to the j. Now we're going to play around with this relationship just a very, very small amount here, okay? But the first thing that I want to do is I want to ask you what we have here, all right? We have on the left-hand side an exponential form complex number, which is equivalent to a polar form complex number because they contain the same two pieces of information, a magnitude and a phase angle. And on the right-hand side, we also have an exponential form complex number, which can be thought of as a polar form complex number containing only a magnitude and a phase angle. So on the left-hand side, since the only information that we have is Vm and theta V, this is exactly our phasor voltage V. On the right-hand side, we have R times Im e to the j theta I, which is exactly our phasor current I. So we have developed a frequency domain or phasor domain relationship. Okay. So Ohm's law in the frequency domain is the exact same thing as Ohm's law in the time domain. Shouldn't be that big of a surprise because of how resistors behave. We can observe a couple of things from this relationship, right? Our magnitude, Vm, is going to be the exact same, our magnitude on the left-hand side has to equal the magnitude on the right-hand side of the equal sign, which means that Vm, the magnitude of our voltage, is simply R times Im, the magnitude of our current. Another thing that we can notice is that the phase angle on both sides of the equal sign also have to be the same, because these are two complex numbers that are equal to each other, right? So if the phase angle on the left-hand side is theta V, and the phase angle on the right-hand side is theta I, that means theta V has to be equal to theta I for a resistor, which means that a resistor does not introduce any sort of phase shift. Okay, and we'll talk about what that means a bit more when we get into our discussion of actually analyzing circuits. Okay. So these are our phasor relationships for resistors. We have our generic relationship, phasor voltage V is equal to R times phasor current I, just good old Ohm's law. We know that the magnitude of the voltage drop across a resistor is equal to the resistor value times the magnitude of the current flowing through the resistor. And we know that the phase angle of the voltage and the phase angle of the current have to be the same thing. Now let's talk about what happens with an inductor. Where I have a voltage V of t like so, and a current I of t like so. And I'm going to scroll up here, these exact same definitions for voltage and current that we did for our resistors. I'm going to use the exact same thing, so I'm not going to bother rewriting that big long thing down over and over again. Okay. So what's the relationship between voltage and current for an inductor? Right. So Michael suggested that we use the relationship V of t is equal to L di by dt. And that's exactly what we're going to use. We're going to use the derivative-based relationship because it's going to make the math a little bit easier on us. Okay. So this would look like Vm e to the j omega t plus theta v is equal to L times the derivative with respect to time of Im e to the j omega t plus theta I. So on the left-hand side, we'll keep Vm e to the j omega t plus theta v. On the right-hand side, I believe we figured this out in Monday's class meeting, that when we take the derivative of that exponential function, we're going to wind up bringing down a factor of j omega, right? So this is going to look like j omega L times Im e to the j omega t plus theta I. I could split my exponential function up into the frequency component and the phase angle component like I did previously, and then wind up just canceling out my frequency component. which would leave me with Vm e to the j theta v is equal to j omega L times Im e to the j theta I. Okay, so all I've done between these two steps is get rid of that common factor of e to the j omega t that's on both sides. Now, we are going to manipulate this expression in a minute, but from this, we can get our most generic phasor representation, right? On the left-hand side, we have our phasor voltage V, and on the right-hand side, we have j omega L times our phasor current I. Because anytime we have a magnitude and a phase angle, we have a phasor. So I'm going to do something up here really quickly. If this is my, so excuse me, this should be my imaginary axis. This is my real axis. If I go out, let's say 1 unit in the real direction, this is simply the number 1. In rectangular form, this is 1 plus j0. And in polar form, or exponential form, this is 1 e to the j 0 degrees. If I go up 1 unit in the imaginary direction, this is simply j, or 0 plus j1, or 1 e to the j 90 degrees. If I go 1 unit in the negative real direction, I have -1, or -1 plus j0, or 1 e to the j 180 degrees, and that could be plus or minus 180. And then finally, if I go 1 unit down in the imaginary direction, that's going to look like -j, which is the same as 0 minus j1, or 1 e to the j -90 degrees. So minus j 90 degrees. Okay. The reason why I'm pointing this out is because we are multiplying this bit right here, omega L Im e to the j theta I, by j. Well, if we express j as 1 e to the j 90, this becomes omega L Im e to the j theta I plus 90 degrees. From this, we can see that Vm is equal to omega L times Im. The magnitude of the left-hand side has to equal the magnitude of the right-hand side. And we can also see that theta V is equal to theta I plus 90 degrees. So for an inductor, the current always lags the voltage by exactly 90 degrees. We are going to do a lab next Monday that will physically prove this. All right, so before we move along to capacitors, does anybody have any questions about our inductor relationships?
Not a question about that, but I was trying to do the BC problem up at the top. How do you put that into your calculator?
Let's wrap this up and then I'll show you. It'll be better. Yeah. All right. So let's look at a capacitor. And let's go to the next page because I'm not 100% sure I'm going to have enough room there. So for a capacitor C, with a voltage V across it and a current I flowing through it, using the derivative-based relationship, again, purely to make our math a little easier, we know that I should be equal to C dV by dt. It says I am e to the j omega t plus theta I is equal to C times the derivative with respect to time of Vm e to the j omega t plus theta v. When I take the derivative with respect to time of that e to the j omega t plus a phase angle, that is again simply multiplying by a factor of j omega. And so that's going to give me I am e to the j omega t plus theta I is equal to j omega c Vm e to the j omega t plus theta v, which is the same as I am e to the j theta I is equal to j omega c Vm e to the j theta v. And so we'll get our relationships. I'm going to go ahead and also express this as omega c Vm e to the j theta v plus 90 degrees. Doing the exact same thing we did with our inductor, so I feel like I don't need to explain how I was able to do that again. So on the left-hand side here, we have phasor current I is equal to j omega c times phasor voltage V. And using these relationships, we can see that Vm is equal to Im divided by omega c. And we can see that theta I is equal to theta V plus 90 degrees. So these are our frequency domain relationships for resistors, inductors, and capacitors. Okay. Anybody have any questions on this before we move on to our next kind of miniature topic for the day? All right. So the next thing that we're going to talk about here is the concept of impedance. So on our third day of class, I expressed to you all definition of resistance. Okay. So if we had a DC black box network, really wouldn't particularly matter what was inside it as long as it was full of linear elements. And we applied some DC voltage. If we measured the voltage drop across the terminals of our network, and we measured the current flowing into our network, we found that resistance R was simply the ratio of the voltage across the terminals of the network divided by the current flowing through the network. I made you guys do an experiment to prove this as well on the second day of class. So impedance is the AC circuit equivalent. Okay. So if we take our black box network and we apply a phasor voltage Vs, okay, which is just our way of representing a sinusoidal voltage signal, and we measure a phasor voltage V across the terminals of our network and a phasor current I flowing through the terminals of our network, we can define a quantity called the impedance Z, which is simply the ratio of the phasor voltage V over the phasor current I. So impedance plays the role of resistance in AC circuits. Okay. Now, impedance is a ratio of complex numbers because our phasor voltage V is a complex number and our phasor current I is a complex number, which means impedance must be a complex number as well. So we can express it as either a polar form complex number or a rectangular form complex number, right? So let's just manipulate this a little bit here and get our polar form relationship. So we'd have Vm angle theta V divided by Im angle theta I, which would be the same as Vm over Im angle theta V minus theta I, or the magnitude of our impedance Z with a phase angle of theta Z. So there's where our polar form complex number representation comes from. All right. Rectangular form representation would be our magnitude cosine theta Z plus J magnitude sine theta Z, where this real part we call resistance, and this imaginary part we call X, or the reactance. Okay. Now, the resistance portion of impedance is caused by the presence of resistors. The reactance portion of impedance is due to the presence of inductors and capacitors. Okay. And so I'd like to explain that to you. So let's say that we have a resistor. Go back in your notes, like a page or two from when we were developing our phasor domain relationships, and tell me what phasor voltage V divided by phasor current I should give me. for resistor. Pardon? Just resistance, R, absolutely right. So the impedance of a resistor is just the resistor value itself. We can express this more formally as a rectangular form complex number. Actually, let me do it as a polar form complex number first. R angle 0 degrees, or R plus J0. So refresh my memory, what are the units of resistance? Ohms. Okay. If we have want to determine what the impedance of an inductor is, go back in your notes and simply tell me what the ratio of V phasor divided by I phasor is. J omega L. So as a polar form complex number, that's going to look like omega L angle 90 degrees, or 0 plus J omega L, right? So an inductor does not contribute any real portion to the impedance. It only contributes to the reactance portion, and it contributes positive reactance. Now let's talk about the units for this, okay? So the units for radians, or excuse me, for omega is radians per second, where a radian is a dimensionless quantity, okay? The units for inductance is the Henry, which is a volt second per ampere. So we can see pretty easily that the seconds and the per seconds cancel each other out. Since radians is a dimensionless quantity, it doesn't really do anything. And we're left with volts per ampere, which is the exact same thing as an ohm. Finally, let's look at capacitance. So if we take phasor voltage V divided by phasor current I, what do we get for our capacitor relationship? 1 over J omega C. Right. Which is going to look like 1 over omega C with an angle of negative 90 degrees, or 0 minus J times 1 over omega C, where I'm using the fact that 1 over J is the same thing as negative J, which we discussed when we did our complex number review, I guess last Friday, whatever day that was. So dimensionally, we have 1 over radians per second times 1 over farads, where a farad is an amp second per volt, right? So we have seconds and, excuse me, per seconds and seconds canceling each other out. The radians don't do anything, and so we have 1 over amps per volt, which is the same as a volt per amp, or no. So we have now expressed our 3 different impedances, one for resistance, one for inductance, and one for capacitance. And we have observed a couple of things, or I have observed a couple of things, and I'm going to tell you what those are because you may not have caught on here, okay? So the first thing is very, very important. Since all three of these impedances have the same units, that means effectively that impedances combine like resistances, okay? So all of our simple resistor combination techniques that we developed way back at the beginning of this class are now applicable to be used for impedances. So we no longer have special rules for inductors and capacitors. We just have effectively AC resistances that combine just like DC resistances, okay? Another thing that's maybe a little more subtle is that the impedance of a resistor is independent of frequency, meaning it's the resistor value is the impedance. It doesn't matter what frequency we're operating at. The impedance of a capacitor and the impedance of an inductor, however, are frequency dependent. So let's take, for example, an inductor. At very low frequencies, so when omega is very close to zero, what does the impedance look like? Substitute in zero. Zero. Or what does an impedance or a resistance of zero mean? A short circuit. For our capacitor, what happens when omega is very close to zero? We have 1 over infinity, or excuse me, 1 over 0, which looks pretty much like infinity, so the capacitors behave like an open circuit. Everything that we're doing here directly matches everything that we've done previously. What's particularly interesting, though, is that at very high frequencies, inductors start looking like open circuits, and at very high frequencies, capacitors start looking at short circuits. So their roles reverse, and it's because of that frequency dependence of impedance. This property of frequency dependent impedance is how electrical filter circuits work, or how we pass certain portions of signals and attenuate other portions of signals. That's kind of beyond the scope of this class, but for those of you who go on into doing more with circuits, so probably definitely the electrical engineers, the majority of you biomedical engineers, and some of you mechanical engineers will kind of revisit this from the concept of filters later. All right, so we are now ready to do circuit analysis in the frequency domain. And so what I'm going to do here is we're going to rehash that same problem that we did on Wednesday that took us 35-ish minutes the first time and about 5-ish minutes the second time. And we're going to be able to do it in about 40 seconds here now. Okay. So we had a voltage source, Vs of t. We had a resistance R that was what, 10 ohms? We had an inductance L that was like 1 Henry. And we were trying to find our current I of t when Vs of t was equal to 8 cosine 2t. Did that summarize what we looked at on Wednesday, or Monday, excuse me? I believe I've got all the numbers correct. Okay. So what we're going to do is we're going to take this circuit in the time domain and convert it into the frequency domain, which means we're going to represent our voltage and current signals with phasors, and we're going to represent all of our resistors, capacitors, and inductors with their impedance. So how do I convert 8 cosine 2t volts, my time domain voltage, into a frequency domain voltage? 8 angle 0, absolutely right. 8 angle 0 degrees volts. My current, I'm going to represent by a phasor current I. What's the impedance of my 10 ohm resistor? 10 ohms. What's the impedance of my 1 Henry inductor? So J times omega times 1. So what's omega? 2. So J times 2 times 1 is J 2 ohms. And just using good old Ohm's law, I can see that I is equal to 8 angle 0 degrees volts over 10 plus J 2 ohms, which comes out to be 0.784 angle negative 11.310 degrees amps. And converting this phasor current into the time domain, I get 0.784 cosine 2t minus 11.310 degrees. So we boiled down 35 minutes of trig and calculus into several seconds worth of algebra by analyzing this circuit in the frequency domain as opposed to the time domain. So this is obviously the methodology that we're going to take when we have any steady state sinusoidal circuit to analyze. Okay. All of the DC relationships that we developed in the first third to half of this class can be applied to steady state sinusoidal circuits in the frequency domain. We can use Ohm's law, KCL, KVL. Impedance combination follows the exact same rules as resistor combination. We can do voltage division, current division, superposition, nodal analysis, mesh analysis. We can use Thevenin equivalent circuits. We can use Norton equivalent circuits. We can do source combinations. We can do source transformations. Everything that we learned in the first section of this class now comes to us again to be used. The only caveat here is we have to do it using complex numbers. But all of our basic circuit analysis techniques are now valid as long as we work in the frequency domain. Okay. So I have an in-class assignment for you guys. It's only 2 problems long. And the first problem is literally a pretty basic circuit. And I ask you to analyze it however you feel like it, because literally any method that you're comfortable with will work. Okay. And then there's also a second problem. On Monday, what I intend to do is to review some things, some of the circuit analysis techniques that you guys feel less comfortable about for about an hour. And then we're going to have a lab, okay? So in order for me to review the circuit analysis techniques that you guys are the least comfortable with, you have to tell me what circuit analysis techniques you're the least comfortable with. So what would you like me to review? Superposition, okay? Voltage and current division, all right. So and Thevenin and Norton equivalent circuits. Okay, so I feel like that's probably pretty close to an hour. So superposition, voltage and current division, Thevenin and Norton equivalent circuits. We will redo those in the frequency domains. We'll get some practice playing around with complex numbers, and then we'll wrap things up with a lab on Monday. Does that sound good to everybody? All right, so I am done yammering for today. So take the next roughly hour and work on this in-class assignment. If you have any questions or anything, I'd be happy to help you out.